We have learned about testing, about rejection regions, about those alpha, n, sigma, whatever. So now in this video, I'm going to make an experiment. The reason to make this video and this experiment is to try to make the concept of hypothesis testing clearer. And in particular, our focus will be on the type 1 error. So let's very quickly review what is type 1 error. So let's go back to our slides. Basically, we're saying that whenever we are doing a statistical hypothesis, we have hypotheses like this. We have null hypothesis and we have alternative hypothesis. We say that we're going to make some default assumption on the unknown. Let's assume mu is 1. And then we try to collect some sample, we try to find some evidence, and we see whether the evidence is strong enough to reject our null hypothesis. Okay? And then that type 1 error is, what's the probability? Type 1 error means the error we make when we say the null hypothesis is wrong, but actually it is right. Okay? It is right, but we say it is wrong. That's type 1 error. And the whole thing that we are constructing is a system that when we reject H1, when we reject H0, we control its error probability. We control the type 1 error probability. Okay, so I'm going to use this experiment here to try to convince you that we are really controlling that type 1 error probability. So let's see what's this. So I still have these numbers. My population is a is a distribution where the mu is 1000 and the sigma is 200. Okay, and to make the experiment easier, I'm going to assume that the population is also normal. And then I'm going to do this. I'm going to say, okay, I'm going to do a lot of experiments, or you can say I'm going to collect a lot of samples. Today, I collect a sample with 100 as the sample size. Tomorrow, I do it again. I do a random sample again and get a sample whose sample size is another 100. So every day, I do a different sampling process and I get a different sample. So for example, day 1, I get numbers like 1019, 919, 1242, and so on and so on and so on. So these numbers that I'm selecting are the 100 sampled values in my first day sample. And then I have my second day, and for the second day, I get the random samples again, another 100 numbers. Okay, so now very quickly, let's take a look on how I get those samples. Basically, what I'm doing is that I first tell the normal curve that I'm going to randomly select a place as the cumulative distribution, cumulative probability. So like say 0.8, 0.2, 0.9, somewhere. I know somehow this number must be between 0 and 1 on the probability. So that's why I use rand to randomly generate a number that is between 0 and 1. I take that as the left tail probability. Then that's going to allow me to use this normal inverse function to revert back to a normal random number. Okay? So for example here, why I get 871 is because that for this rand I get a small number, maybe just 0.2 or 0.3 or 0.1. So that's why I get a number that is below 1000. Why here I get 1110? Because I get a random probability, left tail probability, that is 60% or 70% or something. Okay, so with this, we're going to generate a lot of values that are actually normal. So if you want to have some visualization, you may randomly select a few numbers here and try to draw a histogram. Okay, you see that, well, it's indeed somewhat normal, right? And because we are doing everything using the rand function, you press F9 or you redo all the experiments, we're going to see that the numbers that I select are changing, but basically it's normal. So anyway, that's how we get a lot of normal random numbers. So now you may assume that we have a very large normal population, and we select 100 numbers first day, another 100 numbers second day, and we do that for 200 days. Okay, so I do this process repeatedly for 200 times. For each time, I of course calculate my x bar, which is the sample mean. Okay, in this large population, I randomly select 100 numbers, and then I do the average. That's my sample mean. So if that's my sample mean, then we're doing hypothesis testing, right? If that number is quite large or quite small, that's going to make me reject our null hypothesis. Okay? Previously, we have our rejection region. If we follow the settings in the slides, then basically our alpha is 5%. Rejection region is about two thresholds, 960 and 1039. So here, if this number is less than 930, reject. 968, reject. If this number is above 1039, reject. Okay, so this is not. Are we rejecting? We may use this OR function to combine two conditions. We will ask, is this number lower than 968? Or is this number is greater than 1039? If any of them is true, we label it as 1. Otherwise, we label it as 0. So you see a bunch of zeros here because all these numbers are somewhat close to 1000. But this number, 947, is too slow. It's too small. So that's why it is considered a rejection. Okay, so now this experiment, on day 15, we are making a mistake. Okay, when we are doing all these random numbers, we are using a normal random function to get these particular values. So what does that mean? That means we have a population which is normal, and the mean is 1000. The fact is that mu is 1000, but because we are somewhat unlucky, that 100 numbers that in our random sample are somewhat just small, so small. So we make a wrong decision. The population mean is indeed 1000, but we say it is not. This is type 1 error. Okay? We want to use that 200 experiments to see whether the probability for us to make type 1 error is under control. So roughly we can see, okay, a lot of zeros, so we're not making mistakes a lot, and sometimes we get 1, but most of the time we are getting 0, right? So basically what we want to do is that, why don't we just sum of them? Because we have a bunch of zeros, some ones. If we have the sum here, that is the number of errors, number of type 1 errors we make during that 200 experiments. Okay? Or if we divide that number by 200, then that's exactly for each random sample, what's the probability for me to make that mistake. Okay? So if we repeatedly do this, we can see that the probability is typically around 5%. So sometimes it's 4, sometimes it's 2, sometimes it's 7. Of course, you may see some number that is above 5% because we are just having 200 experiments. If I do 2 million experiments, 2 billion experiments, you will see this number exactly, I should say almost exactly 5%. Okay, but because we only have 200 experiments, so that's why sometimes you still see a large number. But for each independent experiment, before you do that experiment, that theoretical type 1 error probability is 5%. And how may we confirm that? That's the reason of this experiment. So you won't see that this probability to get to too high. If this is not 5%, then maybe you are going to see this number becomes 10, 15, 20, whatever. But no, because we set alpha to be 5%. So that's why here, pretty much you get some number that is around 5. So very quickly, we may take a look. How about this? I'm going to set my alpha to be, let's say, 20%. Okay? I want to have a rejection region so that when I make decision to reject my H0, my error probability is no greater than 20%. So if I do that, I have a rejection region that is different, and then I see that I get a lot of errors here. Okay? So now again, we get 20% as the error probability. You change it, you see that numbers are still changing, but it's around 20, right? It's around that 20% you set. So because you are using a different alpha, different requirements for controlling your type 1 error, so your rejection region becomes different. It's more likely for you to make that rejection decision. And of course, then it's more likely for you to make a mistake. Okay? So that's why we have this type 1 probability, and that's why we have to set this alpha. Then of course you may want to ask, well, then what's the point of having a large alpha? Because if your alpha is very, very small, then your rejection region will be very, very small in some sense. It will be very unlikely, quite unlikely for you to make a confirmative conclusion. And you know that if you don't reject H0, basically you have no conclusion. And this experiment is not telling you anything. Okay? So in practice, people need to make some reasonable decision about alpha. That's why it's typically 5%, 1%, 10%. Okay? So I hope this experiment somehow helps you to understand more about testing, about type 1 error, about all the settings here.